So the introductory course on analog and digital electronics. It's a very interesting course, which is ESC 301, and it will give you a very clear insight on how actually the analog and the digital world coexists and facilitates communication along with the ideas. My name is Shivcharan Puri, and I am from the Department of ECE, Asansol Engineering College. So this is the textbook which you can refer to. So Microelectronics Engineering for analog portion, Cetran Smith, good book. You can also use this as a textual book. Principle of Electronic Devices and Circuits, B.L. Thareja and Seda. Digital Electronics Karate, you can use it for digital part. RPGen, you can use it for digital part. Now the introduction. So you can see you'll come across all these keywords, across this whole course of ESC 301. Digital quantities, analog quantities, binary digits, bit, pulse waveform, clock, timing diagrams, data, serial, parallel, input, output. So digital and analog quantities. So you can see introduction. Electronic circuits can be divided into two broad categories. One is digital and another one is analog. So digital electronics involves quantities with discrete values, and analog electronics involves quantities with continuous values. Although you will study digital fundamentals in this book, in this course, it's also important to know about the analog portion. Okay, because because the digital part, you can achieve these digital techniques, okay, by using these analog modules only. Okay, so what is an analog quantity? Analog quantity is having continuous values, okay, takes on all the infinite values in between, say A and B. So suppose if you are visualizing this analog quantity with respect to time, so you have to take the values for each and every moment of time. It exists for each and every moment. Okay, it is having the finite values at every moment of time. But if it is a discrete, if it is a digital quantity, you will be having values at certain instance of time. Okay, so you can see here. So if you plot time of the day, x-axis, and temperature along the y-axis, okay, so as you can see here, analog quantity is continuous throughout the graph. Now digital quantity, that it is actually the most important use is that digital quantity has a set of discrete values. Okay, as you can see here, the same graph for which we require a lot of data, infinite data in continuous domain. In digital domain, we require only few set of data. Okay, so at a certain instance of time, we have to take the data. Okay, and at the receiving end, we can easily get the same spectrum using a filter circuit. So that's what the whole idea of this converting from analog to digital and digital to analog. But digital certainly gives you the better advantage. Okay, because it doesn't use the analog values, rather it uses a digital code, which is based on zeros and one, which we are going to discuss next. Now, example, you can see a public address system, as you can see here, used to amplify sound so that it can be heard by large audience, is one example of an application of analog electronics. So if you can see here, the sound which is coming out, it is reproduced sound wave, and this is an example of an analog. Okay, But you can see here a digital example, computer system. Okay, it's a brilliant example of the application of digital electronics. So you can basically have the values, digital values for all your applications. As you can see here, CD player, again analog one. Okay, but in this particular system, it uses a CD drive. Okay, and CD drive used to give the data, or rather the communication happens over there. Okay, as a digital data. So this is a example. As you can see here, this is again analog, but the whole system is actually a mixed system. Okay, now this is the digital advantage. Digital has certain advantage over analog. Example, digital data can be stored, processed, and transmitted more efficiently and reliable than analog data. You see here a lot of applications, and also after the emergence of this signal processing circuits, okay, which are digital circuits, too much of advantage is there over the rather sustainability over noise, and the encryption and all the security of what I mean to say. So digital clearly gives has an edge over the analog signal. Now let us come to this binary digits, logic level, and digital waveforms. So digital electronics involves circuit and system in which there are only two possible states. These states are represented by two different voltage level. So one is the high and another is a low. The two states can also be represented by current levels, open and close switches, or lamps turned on and off. In digital systems, combinations of the two states called codes. Okay, so there will be a set of arrangement. So suppose if you say it is high, and if I say high is plus 5 volt or 1 in the binary, or rather digital, okay, and if it is 0 volt or rather 0 in digital, so with this 1 and 0 you can have infinite possibilities of obtaining a code, and you can rather stream this code and communication can happen. Okay, so clearly digital is having here also great advantage. Because it is used to represent numbers, symbols, alphabetic characters, and other types of information using the same codes. Okay. So it is a two-state number system, which I call it's a binary, and it is either 0 or 1. Either it is off or it is on. Off can be represented as 0, and on can be represented by 1 in a positive logic system, and contrary, off can be represented as 1 and on can be represented by 0 in a negative logic system. So there are systems in which you can define your digital in which digital domain you are in, you are trying to fulfill your demand, and simply a binary digit is called a bit. So we will stick to this bit, which is a binary digit, either 0 or 1. So as you can see here, this is a binary digit, 0 and 1, very simple. High and low logic levels. Okay, so as you can see here, practical digital circuit, a high can be any voltage between a specific minimum value. As you can see here, if it is a practical circuit, so this can be your 1 and this can be your 0. Okay, and this is unacceptable because there has to be a difference between these high and low in a practical circuit, because it is linked to the voltages. Okay, so in logic families chapters is there, which we will discuss in some time. In that we are going to discuss all about this now what is this basically highs, how this high is basically represented, low is represented, and what is the noise level, or the noise margin, propagation delay is there, and fan out, fan in, lot of things are there which we are going to discuss in the near future. So as I told you, this is a positive logic system. 0 is low and 1 is high. 0 is for 0 volt and 1 is for plus 5 volt. And this is the negative logic system, where the contrary happens. 0 becomes high and 1 becomes low. 0 volt becomes 1, and plus 5 volt becomes 0. So this is a typical example of code. So with this 0 and 1, you can go and build up your own code, okay, which will perform a specific function. You can also is used to represent number, letters, symbols, instructions. Okay, ASCII is one of the brilliant example which we are using in our keyboard and all these things. So we have to code it, and accordingly our keyboard will work. That we will be studying one of the case in the combinational logic chapter in the near future. So as you can see here, what is the code? I mean the mnemonics, the symbols, and what is the corresponding binary values. So you can code each one of this. So if it is, you can see here. So if it is a code A, capital A, then the decimal value is 65, but the code is this one. So likewise, you can represent any other things with these binary codes. Of course, great advantage. Now, next thing which we are always going to witness by studying combinational or sequential details is the digital waveforms. Okay, so what is this digital waveforms? So digital waveforms consist of a series of pulses, voltage levels that are changing back and forth between the high and low levels. As you can see here, so this is a digital waveform. As you can see here, so this is a train of pulses. So this is nothing but a clock. Okay, with each clock having with each clock, so time, these are with the time period from on to off. So one time period, so another time period, another time period, because clocks takes a finite time to go on and a finite time to go off. So therefore, this concept has come, and this is periodic. Actually, you can see here a periodic square waves is generated. Okay, and here you can see here it's not periodic. This signal is not is aperiodic, non-periodic. Okay, so these two types of signals you will always come to see in the near future. Okay, so this is basically digital waveform. So you can see here the pulse train of the digital waveform. It is a continuous series of pulses. Okay, and therefore it is known as pulse train. Or idle pulses. A single positive going pulse is generated when the voltage goes from its normally low level to its high level, and then back to its low level, which I told you. A single positive going pulse, so it is go from high. It takes a finite time to go to high, and a finite time to reach low. Okay, so this is a single positive clock. And what about the negative going pulse? Negative going pulse is generated when the voltage goes from normally high level to its low level. Okay, so the reverse happens. Okay, so it will not start from here, rather it will start from here, then in here, again it will go. Okay, so this is the, as you can see, so this is the positive going pulse and this is the negative going pulse. Okay, so as you can see here it is a rising or leading edge, whereas here is the falling or leading edge. Okay, so if here it is rising, here it is falling, and you can see here it is falling, here it is rising. So negative going pulse. So non-idle pulse. Okay, so this is a basically practical one, because practical circuit uses a filter. Okay, so as you can see here, the time required for the pulse to go from its low high level to high low level is called the rise or fall, rise time or fall time. In practice, it is common to measure rise or fall time, whatever, from 10%. Actually, if it is rise or fall up to 90%. Okay, so as you can see here, if it is rising, we are taking 10% into consideration. Okay, but if it is falling, you have to take 90% of that into consideration. Okay, so this is an example of a practical pulse, or rather than non-ideal pulse characteristic. You can see here. The pulse width is a measure of the duration of the pulse and is often defined as a time interval between the 50% point in the rise and falling edge. As you can see here, this is rising, this is falling, this is the 50%. So this width is actually taken as the pulse width. Okay. So periodic pulse, as I told you in the previous example also. So it is a periodic pulse having a fixed time period. The time period is related to the frequency, as frequency is equal to frequency is the inverse of time period. Okay. So period pulse. Now comes the duty cycle. The duty cycle is defined as the ratio of the pulse width TW to the period t and can be expressed as a percentage, as you can see here. So this is the width of the pulse. Okay, so this is the width of the pulse, and the duty cycle is basically given by basically related with the pulse width and the time period capital T. Okay, now non-periodic pulse, as you can see here, this is a clear, it's a non-periodic pulse. Now a digital waveform carries binary information. Binary information that is handled by digital system appears as waveforms that represent sequence of bits. When the waveform is high, let us straight away go to graph. As you can see here, so this is a clock. As we know, it's a train, so it's a continuous production of a train of pulses. Okay, so this is a clock, on off, on off, on off, and so on. Okay, and this is a bit sequence. Okay, so the when this is, you can see here, when this is 1, when this is 1, you can see a binary 1 is presented, and when it is 0, binary 0 is presented. So each bit in a sequence occupies a definite time interval called a bit time or bit interval. That's what called as a bit time. Okay, the clock. In digital systems, all digital waveforms are synchronized with the basic time waveform called the clock. So it's basically a device which basically syncs a lot of activities using the master control. Okay, so very, very important parameter of the digital domain. Clock is a periodic waveform. It generates a train of periodic rather pulses. Okay, as you can see, it carries so this clock generates the pulses and a lot of digital activities goes around. Okay, so as you can see here, clocks are used extensively in computers. Okay, all processor runs with an internal clock. Modern chips run at frequencies up to 3 gigahertz. This works out to a period as little as 0.33 nanoseconds. So that's what the fastness actually of basically the of operation of the digital circuit. Okay, so in Europe it's used AMD. In India we used to go for Intel. So depending on the country also, there are a lot of processors which uses digital circuitry with the master clock having different frequencies of operation, and which decides rather how fast your PC is. Okay, so a timing diagram is, as you can see here, we talked about timing diagram, as you can see. Okay, so this is a typical timing diagram. Okay, where there are two signals. This is a clock, it generates train of pulses. This is a signal A. This is a kind of output. Don't think that what kind of output that. Just see this output. Okay. So if it is a if it goes to 1, A goes to 1. Okay. And when it is 0, it retains the previous state. And when again it goes to 1, it goes back to 0. So this is the behavior of one of the circuit. Okay. So it is represented as A. Another behavior of this digital circuit is represented by B, and this is the behavior and the circuit C. Okay. So in this way, in sync with the clock, we can get an idea of how the working principle of the circuit, and we will talk about this in great details in the near future. Now, data transfer. Data refers to a group of bits that convey some type of information. Binary data, which are represented by digital waveforms, must be transferred from one circuit to another within a digital system, and from one system to another, because that's the fuel, because that's binary, because data is a fuel. Okay, so that is the only thing by which the whole system actually works. It carries information of everything. Every information is there digitally in a digital system. Okay, for a specific purpose, obviously. Now, serial data transfer. You can see this is serial data transmission is going around, and the most widely used example is a modem. Okay, so there is a computer and it is serially connected to a modem, and your information, whatever you are information you are fetching or providing, are basically serially fed. Okay, so so that means they are sent. So what do you mean by serial? That means they are sent one bit at a time. You cannot send multiple bit at a time because that will be parallel again. So in serial, you have to feed serial bits. That means one bit at a time over a single conductor. So okay, so it's very straight calculation. To transfer n bits in series, it requires n time intervals. Okay. Now parallel data is very fast. The whole of the data, as you see here, the whole 10110010, you can see here, the whole of the data at once, or rather a single clock to be more precise, it's sent to the printer. Here the interfacing is printer. You can think of any other digital interface, no problem. Okay, but it is very fast because it takes only one time interval. So next come the introductory part is the logical operation. Okay, so this is a logical operation. A circuit is there in representation. If it is a switch is closed, you can, the circuit is closed, the voltage will be availed, and you can rather think it as a you can think it as on. And if the switch is off, as we can see it right now, you can consider it as off or zero. On for 1, off for 0. So Boolean algebra, the very important for simplification of the circuits, or rather the logics actually. It was the Boolean algebra simplification logic was given by the Irish logician and mathematician George Boole, and he developed a mathematical system. Okay, and very extraordinary contribution for simplifying the logics. So as you can see here, he provided with the 3 kind of logics. Okay, the 3 kind of logics on which you get a Boolean expression. Okay, and also simplified using the greater contribution from the great scientist. So basically there are 3 kind of operations: and, not, and, or. Okay, the symbols are given by this. So this is not, this is and operation, this is or operation. Okay, so as you can see here, so it is called a gate. So that means it's a not gate, and gate, or gate. Why called gate? Because it will provide the path, or rather it will provide the path, or rather it will give you the access only on the defined level of the logic. So suppose if it is 0 over here, and if this is a NOT gate, you will just get the reverse one. Okay. That means, and that therefore it is also called as inverter. It inverts. On the other hand, if it's an AND gate, okay, so you will get the output if and only if all are 1. Even one is off or 0, you'll get nothing. If it is a OR, the logic goes, any of this is a 1, any. The logic goes like that, you'll get the output. So that's why they are called as gate. So this is the NOT operation. This is the AND operation, as we told. You can see if you're giving 1, you'll get 0. If you're 0, you'll get 1, NOT operation. AND operation, if you give 1, you'll get 1. Okay, because only if one of the input is 0, you'll get, rather if and only if both are 1 or all are 1, only you will be getting the output across the AND gate. Okay, so that is a logic. For OR gate, any of the input is 1. You can see here, if it is 0, here is 1, you'll get a high 1. So that is how the logic goes for OR gate. So the basic logic functions. Okay, and so using this gate, you can you can go for the basic, go for the basic logic functions implementation, that is code conversion and encoding, decoding, data selection using multiplexing, demultiplexing, and the storage you can do. You can go for counters, you can go for comparison using comparators. So a lot of things which you can do using this logic. Okay, so this is a comparator. We will discuss in detail this in the combination logic circuit. Okay, so it compares between this greater than b, between these two, either greater or equal or less, and it will provide you the proper output or the logic or rather the decision. Now similarly for adding and subtraction, both. Now encoding function, as you can see here, a calculator keypad is there. So if this is an encoder, it will give you a binary code. So that's how it goes with the encoder. It will encode the information which you are providing. Okay, and the reverse happens for the decoding. Okay, so if you give a code, it will give you analog output. You can see here. So whatever code will be there, according to this code, it will decode. And 7-segment. This is one of the example for the 7-segment display. Either it will be 0, 1, 2, 3, or so on for up to 8, depending on the binary input you provide. So suppose if the binary input I provide is suppose 3, okay, and suppose I have coded, because you have to code it. Okay, you have to keep the logic. You have to build the logic for this one. Okay, so suppose if I give here 3, that is 0, 0, 1, 1. Okay, and if I decode this information in this particular way, then I will see that this 1, 2, 3, 4, 5, these all 5 LEDs will glow, rest will not glow. So therefore in this way actually encoder and decoder works. Now next is the multiplexer. So among lot of signals, you can be able to select any of these inputs rather. Okay, so this is example of a multiplexer. Demultiplexer, reverse. Now comes your TDM, time division multiplexing. Okay, because multiplexing and demultiplexing are used when data from several sources are to be transmitted over one line to a distant location and redistributed to several destinations. So we require multiplexing and demultiplexing. Okay, and in that the very famous is TDM, time division multiplexing, where we are collecting the data with respect to time, and we are feeding the data in our channel. The storage function, as you can see here, same, using the binary information. These binary bits are stored as memory, okay, using flip-flops, okay, which is actually common. It's not the only memory. There are other type of memories also, but as flip-flop stores one bit information, so it and a group of flip-flops will be forming the registers. So therefore in digital domain you can go for any of these techniques, like using flip-flops, registers, semiconductor memories, magnetic disk, magnetic tape, we know, and optical disks, as you can see here. See, now flip-flops, a bistable bistable state, that can store only one bit at a time, either a 1 or a 0. Okay, so flip-flop basically stores either 1 or 0. But you can see here that's because Q, let us say that Q is our output. Okay, even this is represented in a flip-flop. There are two complementary outputs. Okay, but only one output is taken into consideration. Okay, but anyhow, when we will design the flip-flops, rather logics using sequential logic, we will come across all these things. But right now we only should know that flip-flop is a 1-bit memory. It can either stores 1 or 0 at a time. Register, combinations of flip-flops or rather a combination of 1-bit memory will form a register. So this is one of the example of a register. What is the size of this register? Clearly 4-bit, 1-bit, 2-bit, 3-bit, 4-bit. Okay. So whatever operation it will do taking the 4-bit at a 4-bit under consideration. So this is an example of semiconductor memory, RAM, we know this. Magnetic memories. So as you can see here, typical motherboard. Real, we know this. Counter. Counter is used, is a very important part of the digital domain. Okay. So as you can see here, in counter, there is a counter actually, counter actually counts clock pulses. This is in essence a counter. Okay. Actually, it counts the events. Why? To generate a particular code sequence. Okay. As you can see here, these are the input pulses. Counter is there. Parallel output lines are there. Sequence of binary code which represents the number of input pulses counted. To count the pulse. Okay. So suppose if you are let us so suppose if there's a 3-bit counter. Okay. Or rather, let us say 2-bit counter. Okay. So with 2-bit counter means it will start from 00, 01, 02. Okay. So 4 combinations and 1 1. Again it goes back to 0. That means 0 1 2 3 0, 0 1 2 3 0, 0 1 2 3 0. So in this way, it basically counts the clock pulses and it provides and accordingly it basically runs the application. Okay. Now IC, and so it is very common in digital ICs which we use. As you can see here, inside the IC there is a substrate. It's generally silicon, low cost substrates, and it's made up of transistors, diode, resistors, and capacitors. So these are the typical IC packages. Okay. We will do all this because we require digital ICs 7400, 7410, and so on. We will perform in the lab. So this is one of the more one of the other configuration of the ICs. This actually, just to introduce you the type of ICs. So this is most used DIP, dual inline package. You can see here. Okay, this is too much used. Okay, as you can see here, this DIP ICs, dual inline packages, are most used. You see here, the through hole packages have pins, LEDs that are inserted through holes in the PC board and can be soldered to the conductor on the opposite side. The most common type of through hole package, remember, this through hole package is a DIP. Okay, and this is a this is a surface mount technology. So these are the type of technologies by which you can solder. So you can see here general view. Now this is important, pin numbering while doing the lab. So as you can see here, when you will see this DIP IC, okay, any kind of series, any series, suppose if it is 74LS series or whatsoever, so there will be a notch here. Okay, just remember this notch. Okay, and here will be one small circle, that is a pin identifier. So that means this one which is less distant is 1, and this one which is greater distant to this is the last pin. Okay, so gradually it goes from 1 to 8 and 9 to 16. So this is a way when you will be given an IC, you should not make wrong connections. Okay, because of the wrong selection of the pin, which eventually will lead you to a wrong conclusion. So type of this is actually the type of ICs. It depends on the number of transistor used. Accordingly, you can the gradation has been done: a small scale integration, medium scale integration, large scale integration, very large scale integration, ultra large scale integration, and giga scale integration. Okay. Although there is a limit, it is basically, this integration is nothing but putting number of transistors in a chip, because to perform operation we require more and more of transistor, but you cannot make the size of the transistor very small. Okay, because when you will be making the size of the transistor very small, level can come where you can really touch the nucleus. So therefore it is not possible to reduce the size of the transistor. below the certain point. So as you can see here, type of transistors, okay, because transistors are basically switching devices. So in both ways it is used. BJTs are also used. MOSFETs are also used. MOSFETs are basically metal oxide semiconductor, okay, but practically BJTs are not used because of a lot of limitation. Although the basic principle lies on the bipolar junction transistor logic, okay. It's the best switching device, but right now MOSFETs offer greater advantage compared to BJTs, and therefore also for this integrated circuit technologies, MOSFET is used immensely, okay, which is a great advantage, okay. So a type of digital circuit technology that uses BJTs are TTL, transistor logic, and ECL, emitter couple logic. We will deal with these things in logic families chapter, okay. And for MOSFET, it is either complementary MOS, CMOS, and NMOS, okay. As I told you, LSI, VLSI, ULSI, GSI, the modern integrated circuit technologies uses, as I told you, the uh, metal oxide semiconductor technology. It is cheap and it occupies less area, and also very less power is consumed. That's also one of the most important point compared to the bipolar junction transistors. Thank you so much.